Hi guys, my name is Shashank Kalanathi. I'm a data analyst and I'm on my journey to become a data scientist. And in that journey, I'm going over the book Practical Statistics for Data Scientists. We're going to be going over chapters 1, 2, and 3 as they have a lot of content that is really good for getting a basic understanding of statistics. And a lot of the content that comes after that is actually covered in hands-on machine learning for scikit-learn, Keras, and TensorFlow, which I already have videos for the first 9 chapters in my channel. So go ahead and subscribe and like this video if you're interested in seeing more stuff like this. So before we get started, I actually have notes that I've written out on this chapter and the previous one, and notes on hands-on machine learning. If you're all interested in getting a hold of the notes, then feel free to join my Patreon. It's a great way to support the work that I do and get a hold of these notes. I'll be showing all the notes in this video, but if you would like an actual copy of them, they are available in my Patreon. You'll see that you get access to 12 more posts, including the Chapter 1, Exploratory Data Analysis, which I actually really liked. I thought Chapter 1 of this book was amazing. And up to Chapter 9 of Hands-on Machine Learning, which I might decide to continue that book, but the second half of that book is neural networks and stuff, which I don't find particularly necessary for the work I do currently. And right before we get started, I thought I would also mention that Practical Statistics for Data Scientists has its own GitHub, which has a lot of code inside it. The code I'll be writing is going to be different from some of the code inside the book, and but if you're interested at seeing more of this code, there is a GitHub repo that you can go ahead and check out. All right, without further ado, let's go ahead and get started. Let's pull that up and then go over Chapter 2, Data and Sampling Distributions. So the first chapter was about exploratory data analysis. Chapter 2 I thought was actually kind of very surface level, and it seems that a lot of the content will be going over in more depth than Chapter 3. So this video might not be as long as what I thought, like I think the previous video was like an hour and a half long. So let's just go ahead and get started. The data for the code that I'm going to be writing is available at this link. Go to the NFL Big Data Bowl 2022, and we're specifically going to be looking at the players.csv dataset. That's what we're going to be looking for. And I'm going to be writing the code as we go along because people seem to like seeing me write code live because I tend to look stuff up and I tend to correct myself in person, which goes to show that like in real life you'll be, this is kind of how people actually work. They like correct themselves, they go back, they change stuff. So I will be writing the code live. So the chapter starts by talking about random sampling, and why is sampling at all important? Well, the basic idea behind it is that oftentimes we have data sets that are either so massive or a situation where we cannot gather all of the possible data that we need to actually test a phenomenon. So for example, take something as simple as political polling. It would not be possible to go and actually ask every single, I live in the US, but every single American, what are their political leanings, and ask them every single question about all political topics we might want to know about. So instead, we decided to take a random sample. Now, it's important that these samples are actually representative. There's actually a great story about how, I think it was, who's the guy whose name starts with a G, who's the famous pollster? Gallup. Gallup was able to use a relatively small number of people, but a group of people that were very representative of the American population to poll one presidential candidate winning over whatever the most standard poll at the time was. So it's important to sample correctly. So a sample is a portion of the overall population, usually taken when it is either too difficult to obtain or process the statistics for the entire data set. That can actually be another issue where like maybe it's something like clickstreams, or which clickstream data is basically like when you go to a website, like they'll register all of the clicking data that you do on that website. There might just be too much data to reasonably process, and therefore you just take a sample of the data. The population refers to the totality of the data set available. N is a common variable we use to denote population size. Random sampling simply creates samples by randomly picking portions of the population. Stratified sampling is really interesting. It's when you split the total data set into strata and then take random samples from those. So a common example would be splitting the population by age. So yeah, splitting the population by age. So maybe like buckets of under 18, 20 to 30, 30 to 40, 40 to 50, 50 to 60, and then randomly sampling from each of those strata. So let me go ahead and write that in there. An example would be splitting the population by age groups and pulling data, and randomly pulling samples from each strata. And then a simple random sample samples results without breaking them into strata. Let's see, and then let's move that up there. Stratus is just the groups that data is split into. Actually, I'm probably just going to get rid of that. So you'll actually notice that I don't cover every single bit of content inside the textbook, and the reason for that is I find some of it is either a bit pedantic or unnecessary, and so you'll see I cut out some stuff here and there. I go through the notes a couple of times, and I usually cut out information I don't see as particularly necessary, because I think it's just better for you to know what is actually important. Bias is any systematic error. Sample bias is when you have a sample that misrepresents a population. So, for example, polling one city in America when you want to understand the political leanings of the entire country. So, for example, if you were to only poll Baltimoreans, or is that what you call them? People from Baltimore, basically. When you want to understand who's going to win the presidential election, just polling Baltimoreans is probably not going to give you the best idea of what actually the country thinks. X bar, so let's say pronounced X bar. It is the mean of our sample, and then mu is the population mean of the sample. So these are just some terms that we have to learn. Random sampling, again, this is a fairly simple concept. We'll actually go and write some code to actually go sample some stuff a little bit later. Yes, so just one more section of just notes and stuff, and then we get to actual code. So selection bias is any bias that results from how observations in data that we... it's bias that results from how observations in data were selected. So it's somewhat similar to sample bias, and it can be something like... So bias that results from how observation in data are selected. What would be an example of that? Yeah, I guess it would, like our Baltimore example would also apply to this as well. So, and then, yeah. So I think that would actually probably be one of the best ways to illustrate it. Data snooping is searching through data in order to find something interesting within it. So this is why to prevent this, it's important that you not look through all of your data before modeling. Exploratory data analysis is useful. It's good to understand some aspects of the data, but they also say that, let me rephrase that. To prevent this, it's important that you split apart a section of the data so that you have a section that you're not looking at prior to modeling that you can test your model on. Test set. Yeah, so let me explain what we're doing over here. So when you create a machine learning algorithm, right, you normally split your data into something called a training set and a test set. You, of course, do need to actually look at the data to understand what might actually make the most sense to do with your data. Excuse me. But but what you want to do is you want to split your test set away. That way you have a section of the data that you're not looking at and therefore not drawing too many biases from. So split off your test set and then start looking at your data is a great example of what you should be doing here. Next we have something called the vast search effect, which is a form of selection bias, where one repeatedly runs different models asking different questions on a large data set, which increases the chances that an outlier is deemed interesting. And like I said earlier, one way to combat this is to have a holdout set of data that one can test our conclusions on. So I will actually just copy and paste what I wrote over here. So copy. And this is an example of this. I think the example they gave in the book is that as you start looking through the data, if you keep running tests on it, you might start to see outliers as actually potentially interesting when really they are outliers. So what this is telling us the issue of when you look through data too much to where outliers they're considered interesting when really they are just outliers, and that's not what you want to have. Target shuffling is really interesting. I have a link over here to Elder Research. So this is the guy that runs Elder Research. I think his name is something Elder. Where is he? Maybe he doesn't work there anymore. But he is the one that created this methodology for sampling or of shuffling your target, which basically one way to combat the vast search effect is to shuffle the target variable around so your data is wrong. So basically, you create a model, right? And what does a model do? A model is basically a bunch of x variables that we use to predict a y variable. So create your model, then shuffle all of the y variables around, mix them up to correlate to different sets of x variables. And by doing that, if a model is trained on your x data, then when you shuffle everything around, then the model will now not be really good. So that is one way that you can combat this vast search effect. And then regression to the mean is another concept they go over, which basically refers to the phenomenon that like extreme observations tend to be the ones tend to be followed by ones closer to the mean. And it's important to remember, as without remembering this, it can be easy to assume that an extreme value obtained early on is representative when it really is just an outlier. And one thing I would highly recommend, I would assume some people watch these videos without actually reading the book. I highly recommend reading the book. I like to think of my videos as kind of like an addition to you reading the book. So you like read the chapter, then you watch my video, and you get, okay, this information is now synthesized, I understand this. And the reason I think that's important is because I don't actually go over every single section of the book. I don't think I would be able to do it just at that level of accuracy. So I do hope that as we're going through these, you're also going through the book yourself. All right, now we get to the exciting stuff where we can actually go ahead and write some code. So sampling distribution of a statistic. So now that we talked about just basically sampling the data, right? Sampling is one thing, but usually what we want to do is we want to start talking about statistics of those samples. So for example, you sample a bunch of data and then you take a statistic like the mean or median from that, and that's called our sample statistic. So when working with large amounts of data, sampling becomes very important. And since a sample is not a perfect representation of the population, we need to understand sampling variability. Like, what is the variability of that sample? If our sampling statistic is gathered well enough, we should really be looking for a normal distribution of that sampling statistic. So in this chapter, we'll be talking a lot about sample statistics, which are basically statistics we gather on sample data. So this includes things like the sample mean, sample median, stuff like that. So for example, and I'll illustrate this in a second, if we go ahead and import our player data, so let me go ahead and create a cell over here. So import pandas as PD, and then we'll call it player data import equals pd.read _ CSV, basically meaning that we're reading the player data. Players.csv. We're going to be reading in player data. And as you can see, so this is like NFL player data, so NFL National Football League. It's like the American gridiron football, basically. We're going to be doing some stats on this data set over here. We have 2,700 rows, so a good amount of data. And a sample statistic, a population statistic would be like doing a mean of all of the heights of all of these players, whereas a sample statistic would be like taking 10 of them and then running statistics on that. That being said, while we're here, one thing that's important to remember is in sports, oftentimes different positions will have significantly different physical attributes. So for example, in football, running backs tend to be shorter than a lot of other players, like linebackers, for example. And for that reason, you might actually want to take stratified samples, and we stratified by the position. So basically, what is the mean of running back heights versus taking a running back and counting that as, and comparing that to, another position on the field. So that's why we might want to do stratified sampling with this data set. But I think just for the sake of simplicity, we're just going to do random samples. So additionally, we'll be talking about data distributions, which are basically frequency distributions of individual values on a data set. So that means that, for example, say I was a frequency distribution, if you remember from the EDA chapter, last chapter, is basically when I go ahead and I plot each of these values, counting them as one. So for example, just looking at this, looks like if we look at these top 5 values over here, it looks like we have 3 players that are 6'1", 2 that are 6'0", so that means we'd have 3 units on the 6'1" bar and 2 units on the 6'0" bar, and then basically add more and more as we continue to go along. A sampling distribution is basically a combination of the above 2 concepts, and that is a data distribution of all the values of the sampling distribution. So it is basically this data distribution, but we're doing it with the sample statistic. This is where we get into some interesting stuff. So the central limit theorem means says the means drawn from multiple samples of the data when plotted will resemble a bell-shaped normal curve. And we can demonstrate this by taking the mean of samples of 5 to 20 items and plotting them on a bar chart. So this is just code from the book, but what I'm going to do is I'm going to actually go ahead and do it on this data over here. So let's make this a little bit interesting, just to add a little bit of complexity to this video. I want to do it on the heights of the players instead of the weights. And the problem we have over here is you'll see the heights are written in feet and then inches, when what we really want is we want the height written out in a single unit, so either entirely in height or probably more accurately just in inches. And you'll also notice that some of the heights here are written in inches. So let's go ahead and clean up this data if we can, add in a little small little cleaning exercise while we're here. So I'm going to go ahead and create a new column. So let's go ahead and do player. Well, let me rephrase that. The first thing we need to do is we first need to split up this string based on this hyphen value over here, and then multiply the first value by 12, and the second value, just add that to it, because there are 12 inches in a foot. Just out of curiosity, if anyone knows, if you're not from the US, is it common knowledge that there are 12 inches in a foot? Because, obviously no one else uses feet and inches except for, I think Zimbabwe does or something. And I think British people are familiar with the units too. But if you're not from the US, is it just common knowledge that there are 12 inches in a foot? I'm curious. So let's go ahead and do player data import, and then we're going to go ahead and do the height, and then let's go ahead and do dot apply. I think apply is what we use for series. Yeah, a NumPy function that applies to the entire series. Cool. Okay, so now we're going to do a lambda function. So lambda x. Lambda function basically lets us do a function in a single line, and we're going to do, let's see, x dot split, and I want to split by this. So I'm just curious what happens when I do that. Okay, so then we get either one, right? So yeah, so here's what we're going to do. We have to create an if-then statement. So if the length of the array of the list is just 1, then don't do anything. Otherwise, if it's 2, then multiply the first by 12 and add that to the second one. So I need to remember how to do if statements in an array, or in a lambda function. Python if statement lambda. Okay, return value if condition is true, if condition else return value if condition is false. Okay, cool. So so what I want to do is so we're going to do the true condition. Basically, if there's 2, if the array has a length of 2, if the list has a length of 2, then what we want to do is we want to do x dot split and take the 0th amount, so this, and then multiply that by 12, and then add that to x dot split, Control C, 1, and then I need to do, let's say if the length of x dot split equals 2, else I want to do, else it's just x, basically. I think that's it. Oh, close. Okay, so it looks like what happened was this is a string, so it's multiplying it 12 times. So let's go ahead and fix that. And this is an example where I actually might not use a lambda function just because of how, you see it just looks a little bit complicated. So what I actually might do over here is I might actually just define a function. It seems difficult to read, so I'm not gonna. Or you know what? We're already here. Let's just take it home. So the only thing we need to do is we need to add in we need to cast this to a string. I don't know if you call it casting in Python. I know in SQL you do. So just surround everything by string. Oh, sorry, I need to surround it by int because I need to convert it to a number. So change that to int. Change that to int. Cool. So then we need to assign this to a new variable or a new column. So we'll say, and we'll call it height inches. And then let's go ahead and see what we output. Cool. So there's our height in inches. So yeah, we could have totally just demonstrated what we're about to do with these sampling things on the weight column, since that's already like sorted for us. But I wanted to do a little bit of data cleaning. And the thing is, okay, let me see. What if I like zoom out a little bit? Oh, okay. No, never mind. That's too small. So what I would personally recommend, that is, if you were doing this for like a real, like if you were like actually doing this for like some actual project, I think I would recommend against using a Lambda function, just because this logic is a little bit convoluted to see on one line. It doesn't look clean to me. Obviously, we're just doing this for ourselves, so it's totally fine. But I think in a real situation, you might want to actually have different. You might want to create a function and then call that function inside the Lambda function. In fact, you know what, let's not worry about that right now. I'll let you guys figure out how to do that. I don't want to get too distracted from what we're doing here. All right, so let's go ahead and do the next thing. So let's go ahead and do Illustrator central limit theorem. So I'm going to copy this code over here and then change it up. That way it better represents what we want. And then let's just do a quick data prep. Use the below code to prep our data. So let me go ahead and put this code in there. To import and prep our data. That way you can just run this if you're at all interested. Cool. All right, so that way you can run that first and then go ahead and run whatever code we end up writing over here. Sorry, just checking the recording time. Okay, perfect. So import pandas as PD, import matplotlib as plot, and then take different sample amounts, right? Okay, so I just have to replace the data we're sampling from. Okay. So here's where I can. Perfect. This is where I would replace the code in order to actually sample our data. So I'm going to replace this with player data import height in inches. I should just be able to run that. Invalid index to scalar value. Samples out of pen player. Sample X. So let's see what I did incorrectly here. It might have something to do with it being A. Okay, so that worked. And then if I do dot mean, so now I have a mean, but then I don't need this 0 over here. I'm not too sure why that was in there in the first place, but let's go ahead and try this again. Cool. So let me illustrate what we're doing over here. So basically what we're doing is we're going ahead and importing pandas, importing matplotlib, which is just the plotting library. And then what we're trying to illustrate over here is we're trying to illustrate this point of the central limit theorem, where basically if you take a sample statistic, which means I have all this player data over here, right? I'm looking at the height in inches, and I'm taking the a sample of like, let's say 100 values, right? And I'm taking the mean of that sample, and I record that, and I do that process again and again and again. The more samples I take, the closer to a normal distribution we should get. Or sorry, let me rephrase that. We should get a normal distribution, which if you look at all of these, they're all normal distributions. And as I take more samples, they seem to converge on the same central point, which is probably what the actual population mean is. It's probably about 74. So that's what we're trying to illustrate over here. And let me go through this code line by line. So if you look over here, what we're doing is we're taking sample amounts, and this is just a range function. What this is saying is start at 10, go until 100, and give me a list of values going up by 20. So let me actually illustrate what this looks like over here. You'll see we start at 10, then we go up by 20 to 30, 50, 70, 90, basically up to 100. So that's how many values we're sampling. And you'll see we have the blue stands for anything with 10 samples and 30 samples and 50, 70, 90, so on and so forth. And then what we're doing is we're saying for x in sample amounts. So this is just a for loop. So for each of these values in sample amounts, samples equals just this blank list I created. And then for I in range 1000, this range 1000 refers to the number of times we're taking a sample, right? So we're using this sample function over here to sample, either 10, 30, 50, 70, or 90 values, and we're doing that 1,000 times, and then plotting all the results on this graph over here. That's all we're doing. So let me go ahead and copy this, and I will go and put that over here. That way you can, if you get the notes on Patreon, you can just go ahead and run this cleanly. And then, as you can see, it looks almost exactly like this, but let me take, or, I'll leave the screenshot as it. Oh, no, the scale's completely different, okay. So what is it? It's like Control-Shift-S. Is it Windows-Shift? It's Windows-Shift-S, okay. So let's go ahead and take that. And then we'll go ahead and put that over here. Control-V. And get rid of that. Cool. So we have our new graph. All right, so that's the central limit theorem. Next, we have something called the standard error. And what the standard error is, it's basically a single metric that sums up the variability in the sampling distribution for a statistic. Remember, these are sample distributions over here. And you can estimate the standard error based on the standard deviation S and the number of values in sample N. And you'll see, basically, if the number of values in the sample equals N, as this gets bigger, this is the denominator, right? If the denominator gets bigger, then the error gets smaller, basically meaning that as we sample more values, the error should get smaller, which makes sense. We're expecting the deviation from the true value, which is what the error is. The error is how far away we are from the true value. We should expect that to get smaller as we sample more and more values. So from the previous example with the central limit theorem, you can see that we have to, that as we increase the sample size, the error decreases as proven in the formula above. And we can calculate the standard error in pandas using this. So I'm going to go ahead and copy that. And then what I want to do, and I just copied this code from the pandas documentation, so I haven't actually tested it out yet. Let's see if it works. Oh, whoops. Huh. Okay, so ran into an error, perfectly fine. Let me type in pd.sem, see what we get. My internet's been really, really slow recently. I do apologize for that. Okay, so dataframe.sem, axis. But if I do the entire data frame, will I get the correct value? I wonder if I can do it on a series. Data frame, let's see if series has anything. Let's see, Control F, SEM. There we go. Pandas.series.sem. Yeah, so I should be able to do PD. And this is a series. Let's see if there's some example code. Oh, my bad. Sorry, the PD is implied. I'm an idiot. Okay, so that's the standard error we have for our data. There we go. I am an idiot. So, this over here, the PD is implied because this is a pandas series. And then the next concept they go over is something called bootstrapping. Basically, drawing new samples is typically seen as very wasteful in modern statistics. which favors what we call bootstrapping. And bootstrapping is a sampling method where we draw resamples from a sample, replace the values in the resample back to the sample, and then draw them again, similar to the code we wrote for the central limit theorem. So, or actually not similar to the code we wrote for the central limit theorem. So let me remove that. That is actually not the case. So what does this actually mean? Okay, so it means this. It means that, okay, I have 3 cables in front of me right now, right? And I want to take, a sample of a bunch of them, right? So in bootstrapping, what I do is I would randomly sample one. I would record whatever value that is, so 6-foot braided cable. I'd put it back in the whole pot, and then I would sample again. Okay, and this is like another 6-foot whatever, but this is a different one, right? And then I put it back in, and then I sample again for the number of samples that I want. Now that means that I can actually take multiple of the exact same one, right? Like I pulled this more than once, and that's what bootstrapping is. Bootstrapping does not accommodate you for a small sample size, but it is a very useful way to get sample statistics on your data. And the big thing about it is that there don't have to be any assumptions about the samples being normally distributed. To be clear, if you want to collect a sample of size n, then you'll pick a value, record it, put it back, then pick another value until you pick n values, meaning you can pick values more than once. And you can implement bootstrapping in Python using sklearn. So here's the code that they gave in the book, but we're going to modify it for our purposes. So from sklearn.utils, import resample for n repeat in interesting. Yeah, the Python code they write in this book is very interesting. N repeat interesting. What is that? Actually, I've never seen this term before. Oh, we'll come back to it. So basically for n repeat in range 1000, sample equals resample loans income. So I'm going to replace this with our player data import height inches. And then we should be able to just run that and see what happens. Oh, there we go. Interesting, okay. So what we're doing over here is... okay, so we created a... There we go. Yeah, so this is an example of a resample, or of a bootstrap. Resample is a word that can be used interchangeably with bootstrap sometimes. And, okay, then we appended the median of that sample to the results data frame, turn that into a series, and then original player data import. So this is the actual median. Interesting, so this is the actual median. This is the results.mean minus player data import. Oh, okay, so what is the results.mean? What are we getting here? The mean of that is 74. So if I run it again, I should get a slightly different value, right? Huh, interesting. What if I only sample 10 values? That's odd. Player data import height inches.median, results.mean minus player data import height inches.median, and then the standard deviation of the results. Oh, interesting. Okay, so every single value in results is 74. Is there something wrong with our code? So for n repeat in range 1000, sample equals resample player data import height inches. Print odd. Okay, so you know what? Let's go ahead and rewrite this code. It looks like whatever is written in the book isn't working too well. So let me go ahead and copy this. This is the part that I'm not too familiar with. Okay, so we took that resample over there, right? And then let's go ahead and do dot median. So this is 74. We keep getting 74 for some reason as the median. The mean has to change, right? Okay, so the mean is changing. Okay, in that case, let's go ahead and use the mean. I'm guessing you know what probably happened. You know what? This is probably what happened. Let's check it out. So if I go to our data over here, our player data import data, and let me go make a quick histogram. So height in inches dot hist. I think I can just do that. I was actually expecting a ton of values to be at 74, but it might be just because the data is so well distributed, we just constantly end up getting 74 as a median. So in that case, I guess the code is fine. Let's just go ahead and use the mean in that case instead of the median. There we go. We're actually getting something interesting now. Okay, cool. And it changes from iteration to iteration. And then I just have to change this to be mean. Yep, so this is an example of bootstrapping. Is it? Wait, original. This is supposed to be mean. There we go. And yeah, and the original shouldn't change because I'm taking the mean over and over again. So this is a better example of how we can bootstrap. Basically, the way the specific data set I was using worked is that I guess that when if you just sample a bunch of values, you're basically always going to get a median of 74. And that's a good example of why a median is considered a robust statistic. It's not affected by outliers and stuff nearly as much, or at all, quite honestly. So that is bootstrapping, and it is a way for us to gather sample statistics without worrying about things like is everything normally distributed and stuff like that. Next, we're going to go over confidence intervals. And what a confidence interval is it's something that's really important whenever you're talking about a sample statistic, because a sample statistic obviously is going to have some kind of an error associated with it, and the confidence interval helps communicate what that error might be. So the confidence level is the percentage of confidence intervals constructed in the same way from the same population that are expected to contain the statistic of interest. So if you give it a second, we'll go over it and it'll make sense. So a confidence interval is the interval that contains X%. Usually we pick 95 to 99. So let's say 95% of the bootstrapped sample statistic we're gathering. And we can calculate it using this methodology. Draw a random sample of size n with replacing, basically bootstrapping, from the data. Record your sample statistic, mean, median, etc. And then repeat these two multiple times. For an X% confidence interval, let's go with 95, right? Trim 100 minus x, so 5 divided by 2, 2.5. So 2.5% of the results off of each end of the distribution. And if we do that right, then that means that the center 95% of the distribution will still be available to us. And then trim points define the bounds of the confidence interval. So basically, the 2.5 highest percent and the 2.5 lowest percent, whatever defines those sections over there, that's our confidence interval boundaries. Because it's an interval, right? So it's defined by its boundaries. And confidence intervals are a great way of determining if more data needs to be calculated or if more research needs to be done into the phenomenon. If the bounds of the interval are too far apart from one another, it can be a sign that not enough data has been gathered. A larger confidence interval can also signal a more variable data set. If you think about it, as we showed over here, as we calculate more and more of the, if we take more and more samples, then we're shrinking down the spread of our data to something more, which is, if you remember, 74 was the mean and the median of our data, which is closer to 74. So that's what we're trying to do over here. We're trying to define how much error, what is the total amount of error we might potentially have with our data, and that's what a confidence interval is helping us calculate. So if we want to use Python to calculate confidence interval, then we can go ahead and use the SciPy package. So SciPy has a ton of statistical information inside it. So let's go ahead and try this out. So if there are fewer than 30 items in our sample, then we can use something called a t-distribution. Otherwise, we can go ahead and use, we can assume that the samples are, if there's more than 30 samples that we've collected, sorry, if there's more than 30 items in our sample, then we can assume that there is that it's a normal distribution and just use different code for that. So let me go ahead and copy this. Oh, did I change this up here? I did, okay, cool. So data, right? Let's say the data equals this, and let's just say it equals the first 20 values. So that is our confidence interval with at a 95% confidence level. So you can see it's anywhere from the height of 71.6 to 74.2, which isn't that much. That's a 3-inch difference, right? So that tells us that, you know, even with just 30 values, even with just 20 values, we're getting a pretty good number. So let me go ahead and copy this. And we'll go ahead and put this in here. And then let's go ahead and copy this code over here as well. And then we'll run this as well. And now we're gonna go mask off and just take all of the data. And actually, in fact, how about this? Let me make this more accurate. We're gonna sample 20 values. There we go. So let's go ahead and sample these values over here. And then we'll go ahead and because we should take a sample. I can't just bring in all the values. So we'll sample 1,500 values. And you can see the confidence interval got way smaller. Now we're, you know what, let's, we're like 0.2 inches in our confidence interval. So this tells us that, you know, by collecting 1,500 records, we have a significantly smaller confidence interval. And depending on how important those 3 inches are, maybe 20 records is all you need, but maybe 1,500 is a lot better. Maybe it depends on the scale of data you're looking at, you know. And that's where, like, you know, with data science, a lot of, it is really important to have a understanding of the data that you have and an understanding of what you're doing. That way you know, okay, is 3 inches a big difference or not? So for example, like, if I was, I don't know, navigating a ship from London to New York, right? A 3-inch difference in course might not make a huge difference. Whereas if I was navigating through the Panama Canal, 3 inches to the left or the right might actually make a big difference. That deviation might be really important, which is why it's important to understand what your data is and what is actually important to you. All right, 42 minutes, let's go. So next we're gonna go over normal and Gaussian distributions. What else do we have? Oh, cool, the chapter's almost over. So next we have normal and Gaussian distributions. A couple of definitions over here. Error is basically the difference between an instance and a predicted average value. Standardized is a method of scaling data up or down such that you can compare it to a normal distribution. And then z-scores basically refer to the number of standard deviations above or below the mean that a value is. And Investopedia has a great article on z-scores. So there you go. QQ plots are really interesting, otherwise known as quantile plots. They can be used to determine if a distribution of values is close to a normal distribution. If the QQ plot is roughly diagonal going to the upper right, then it can be considered a normal distribution. And this plot, what this plot does is it orders z-scores from low to high, plotting the z-score on the y-axis and the x, and plotting the quantile or percentile on the x-axis that the rank value is on a normal distribution. Theoretically, what would the quantile be if the data were normal? So I'm going to go ahead and try creating one of these over here. Oh, did I replace that code up here? Looks like I did. Awesome. Okay, so from SciPy import stats. So this is an example of a normal distribution, and we know it's normal because we literally like told SciPy to import a normal distribution for us over here. But let's go ahead and try it on our NFL data. So, okay, looks like it's just an array of values. Perfect. So what I'm going to do is I'm going to get rid of that, and then it looks like I can just replace this entire section over here. And then, again, the sample values. Stats.probability plot. Ah, interesting. Interesting. Okay. But yeah, it looks like our data is relatively normal. It looks like towards the upper end, it kind of drops off from being normal. I wonder if our histogram supports that. Yeah, it kind of does, because if you look at our data is what you call left skewed slightly. And we're going to go over skew in a second, but it is left skewed data. Okay, cool. Yeah, no, this very much relatively follows a normal distribution. So let's go ahead and bring this in our notes. And this is how I did the last chapter. I was kind of like, I wrote out the notes and then like I did the coding section live and people seem to like it, so I'm going to keep doing this. And I think I like it too. I like to do these, I think people like me doing the coding live because it comes off as more natural, which, I'm totally cool with. It works out really well for me. Next, we have something called long-tail distributions. This is kind of what I was talking about like left and right skew distributions. And this is one of those things that I think instead of like giving you definitions, it's just better to explain with an example. So incomes in the United States, I'm not sure if this applies to other countries, but definitely in the US, they tend to be very right skewed, meaning that a bulk of people fall into the left section of a graph if the, let's call it the x-axis is your income and the y-axis is your, count, the number of people in that income. And what that means is that there is a small number of people with a very large amount of wealth in the US. And to be frank, that actually makes some sense. Like income should be right skewed to an extent because you can't, well, I don't think you can have less than a $0 income. I guess you could have more in interest payments than you bring in income. But for the sake of argument, let's just say you can't have, a zero income. So because there is an absolute minimum, but there is no absolute maximum, it does make sense that incomes are right skewed. I think every country has a graph that looks like this, and the sign of a developed country is that the graph is less horrendously skewed. My understanding is that like in countries that are still developing, these graphs tend to be way, way more skewed to the right. But moving off of that, the basic idea is that the direction of the tail, this is the tail over here, is what you call the skew. So this is a right skew graph. And a lot of income graphs tend to be right skewed. Next, we're going to go over something called the student's t-distribution, which is basically a normal distribution with thicker and longer tails. And this is the distribution that sample statistics tend to follow. And as you take more samples, the distribution will more closely resemble a normal distribution. And that makes perfect sense. If you remember up here, that's basically what we, That's basically what we examined. That's basically what we proved out over here. As you take more and more samples, like the tails start to come in and they get thinner and it, more closely resembles a normal distribution. So we kind of like proved that with the central limit theorem. So I'm actually gonna write that note over here. Remember the graph we created with the central limit theorem. All right. And you can go ahead and simulate a t-distribution using this code over here. I'm actually going to remove this because I don't think this is actually useful for what we mostly do. So I'm removing that code over there. And you might be wondering why is it called a student's distribution or student's t-distribution, and that's because it was created by this guy named W.S. Gaussian, who was working for the Guinness Brewery. And at the time of its creation, the Guinness Brewery didn't want people to know they were using statistics to brew their beer, and so they made him publish his work under the name student. And probably the last important thing we go over in this chapter, there's a couple more important things. The one thing we go over in this chapter is the binomial distribution. And binomial distributions are very important to data science because a lot of data science is answers like binomial questions, like buy, don't buy, sell, don't sell, click, don't click, So like, for example, if we use this button over here, the user will either click or they won't click. So a lot of these decision points, which a lot of decision points come down to making one of two decisions, can be modeled with a binomial distribution. And so basically what a binomial distribution requires is it asks us All right, sorry about that, guys. So I did a little bit of research and just had a major brain fart. Basically, in a binomial distribution, there are three parameters that we need to fill in. And over here, you can calculate it using the stats library, the scipy.stats library. And basically 2 refers to the number of successes we'd like. And I'll go over an example of this in a second. 5 is the number of trials we're conducting, so n over here. And then 0.1 is the probability of success of each trial. So for example, let's say we're looking through a website, right? And we want to know what is the probability that we'll make a sale, defined as or let's take it back. What's the probability that someone will click on something, given that we know that there's a 0.1 chance that someone will click on a certain thing, given 5 users. So in this situation, we want to know what is the probability of 2 successes, 2 clicks, given 5 users visit the website, and the probability of any individual user clicking is 0.1. And what the PMF does is the PMF gives us it's a probability mass function, and it gives us the probability that an event will happen that exact number of times, versus the CDF, which is the cumulative density function, tells us the probability that that will happen that number of times or less, So if we wanted to know, for example, what's the probability that it would happen that number of times or more, at least 2 clicks, then we could do 1 minus the CDF. Actually, what we would want to do is we'd want to calculate the CDF for 1. That way, because the CDF also includes the actual value itself, and then anything above that, seeing as you can't do like a half click, would be what we're looking for. So that is a binomial distribution. So if you're doing like A/B testing and stuff, this actually might be quite useful for you. Chi-square distributions, a lot of this stuff is covered in more depth in chapter 3. It looks like they just kind of go over them, they kind of gloss over it. It's a statistic that measures the extent to which results depart from the null expectation of independence. In other words, it's a way of testing abnormality. An example of this was, I used to work at a company where a factory would produce certain widgets, right? And we had an issue where we were getting a lot of warranty returns. Like people perceived that we were getting a lot of warranty returns on those widgets, and we could use a chi-square distribution to determine, okay, is any one factory, significantly different than another one in the expected number of warranty returns. So this factory has a worse performing manufacturing process than like another one. An F distribution, similar to ANOVA testing, measures the ratio of variability between group means and the variability between each group, and lets us perform an ANOVA test. Again, they don't go over it in much depth in this chapter. Like they say some stuff about it, but it's nothing like really actionable. I'm thinking in chapter 3 we're going to go over it in more depth. And then there's Poisson distributions, which simulate the probability of a certain number of events happening in a given time or space, given that we know the average number of occurrences of that event in a certain time or space. A great example of this is traffic lights. So for example, what this code tells us is this code is asking us, if we wanted to simulate the number, let's take a call center, right? The number of calls received by a call center each minute of a 100-minute interval, if we know the call center receives about 2 calls per minute. That we can model that using this. And then now we can use something called the exponential distribution. Let me try this. It'll make more sense for me to put this over here. The exponential distribution is kind of like just the exact converse of the Poisson distribution, where it's the if we wanted to simulate the number of minutes between each phone call, assuming we receive 0.2 calls per minute. That's what this would be. That's an exponential distribution. And then finally, they go over the Weibull distribution, which is, as we mentioned earlier, the Poisson and exponential distributions are only useful if the number of occurrences of an instance, so every phone call you receive at that call center, is independent of all the other phone calls. So presumably the people calling the call center aren't all colluding with each other to call a call center all at once. And each call is independent of another thing. But say you're doing something like you want to determine the number of failures an engine will have over time. Well, engines and other mechanical things tend to fail more often as time goes on because of just regular wear and tear. So because of that, we might want to use a Weibull distribution, which has something called a shape factor, which allows us to model out things like failure rates. And that way we can see, okay, how often do we expect an engine to fail every 100,000 miles or something like that. So to simulate things like this, we use a waveful distribution, and then it's an extension of the exponential distribution, where the even rate can change through a parameter called the shape parameter, beta. If beta is greater than 1, then the probability of an event happening increases over time, and if it's less than 1, the probability decreases over time. So for example, if we're talking about like engine failures, the beta would be greater than 1 because the probability of an engine failure increases over time. And there's also a scale parameter, I think it's called, no, not nu, it's called eta. It's called eta, which is affected by the unit of age, and that can be like, hours, miles, cycles, etc. And the above code simulates 100 lifetimes with a shape of 1.5 and a characteristic life of 5,000. And that's chapter 2 for you guys. Thank you so much for watching. If you like what we had over here, feel free to like, comment, and subscribe. My Patreon is a tremendous way to support the work that I'm doing over here. I love sharing this with you guys. I do a live stream every Thursday and Friday where I answer questions about what life as a data analyst is like. I like to think that the content we're putting out over here is a little bit different than a lot of the other content on YouTube. And it is very time consuming to create, but I love creating it for you guys. And this is a great way to show appreciation and also help make this a regular income for me. That way I can continue to do this more often. But thank you guys so much for coming. And if you like the video, please like, comment, subscribe. It's great for the YouTube algorithm. And I hope you guys have a great day.